Hi, everyone, and welcome back. In this video, we are going to discuss Chapter 12, specifically Section 12.1, scatter plots and correlation, and Section 12.2, which deals with linear regression. And so these are the last two sections that we cover in this class for Stats 1020. So taking section 12.1 first, we are going to look at constructing and interpreting scatter plots, as well as calculating and interpreting the correlation between two variables. So we have yet one final graph to add to our uh, arsenal of graphs that we use to represent data. So a little bit of descriptive statistics here. Scatter plots are really interesting because they allow us to sort of compare two variables, and we'll try to understand what we mean by compare those variables in a moment. So first of all, we do have an axis that we have to use, an X and Y axis, and the x-axis is going to be represented by what we call an explanatory variable, and the y-axis is going to represent the response variable. So we remember, I hope, that explanatory variables are independent. They do the explaining, and the response variable is dependent, right? They respond to the explanatory variable. So again, some chapter 1 vocabulary coming back to us. Now, in scatter plots, as the name suggests, the data points are literally scattered. We do not connect anything, okay? So they're literally just a bunch of dots scattered on the paper, and that's fine. That's where it gets its name from. And the plus side to a scatter plot is it allows us to do some comparisons between quantitative variables. And what we are trying to do is to see whether or not there is a relationship between the two variables, namely the explanatory and the response. Now, the type of relationship that we try to look for is maybe something that's linear, maybe something that's curved, maybe something that does not have a particular pattern at all. And if we notice that there is some kind of linear shape, we want to ask questions like, well, how close to straight is it? Okay, does the pattern follow a positive slope? In other words, do the points go up from left to right, or do they go down following then a negative sort of slope? So it's all about understanding this relationship. Is there a linear sort of relationship between the two variables? What we're going to do is look at some data that deals with NFL quarterbacks, specifically the base salary, the number of touchdowns, and I think what we're looking also is at the quarterback rating. But what we're being asked to do in this prompt is to create a scatter plot between the base salary as well as the number of touchdowns. And so the first thing we have to wonder is which of these two variables would be considered the explanatory and which would be the response. Okay, so does the number of passing touchdowns influence the salary, or does someone's salary influence the number of passing touchdowns? If we think through this logically, even if you don't have knowledge of football, one would think that the more passing touchdowns that you throw, perhaps the more money you would make. Okay, seems logical. All right. So what we would do is we would assign the number of passing touchdowns to the x-axis and the base salary to the y-axis, and you see that listed here. And this is what the scatter plot looks like. Now, you might be wondering, well, how did we plot all of these points? You may recall from the math review video that we treat these as XY coordinates. So if we pick on this one for just a moment, this was a number of passing touchdowns of 46, and the base salary was $3 million. And this was Drew Brees' data point. Okay, so that's the XY coordinate. One more, number of passing touchdowns, 29, base salary, $1.75 million. This was the data point for Eli Manning. So that's how we look at this with the XY coordinate. Now, the question is, do we see any kind of relationship here? Well, contrary to what we thought, perhaps increasing the number of passing touchdowns, the more money you get, there doesn't appear to be a whole lot of a pattern here. Maybe something that's decreasing? I don't know. A little hard to sort of see. Looks to be a bit scattered. So we don't really get a whole lot of information then looking at the scatter plot, at least comparing these two variables. So not really sure what we can do. Okay, so let's change the variables that we're looking at. So now we're being asked to figure out what then is the potential relationship between the number of touchdowns thrown in one season and the quarterback rating. Okay, so which is which? Who do we call the explanatory and who do we call the response variable? Well, even if you don't know anything about football, quarterback rating should suggest to you that it includes a number of factors to sort of assess how well a quarterback is. And throwing touchdowns, the number of touchdowns they throw, would have to be a factor in the quarterback rating. So it sounds like the quarterback rating would be responding to the number of touchdowns. So the quarterback rating I'm going to place on the y-axis as the response variable, and the number of touchdowns thrown on the x variable as the explanatory on the x-axis, okay? And here is what the graph looks like. Now, if we look here, we can see much more clear a linear sort of pattern, and it looks like that as we go from left to right, the points are indeed increasing. They are going up. So this would suggest that there is a positive relationship, positive linear relationship between the number of passing touchdowns and the quarterback rating. Okay, so that's how we use the scatter plot to try to see whether or not there's relationships between these particular variables. And so that's what a lot of this slide is telling us about these things that I have just described to us. And so then there is some further discussion that we need. Maybe there is something going on here with the number of passing touchdowns and quarterback rating, right? There are things that are possible with that. Now, when we compare variables and they have a linear relationship in a scatter plot, we often look to see whether or not they follow a straight line pattern and how close of a straight line pattern that they have. And if we notice, just like in the previous example, that we see that there is some sort of positive slope, right? The line is increasing from left to right. Those data points are following a line. We extend this to say that there potentially could be a positive linear relationship or association. That's the wording we use here. Positive linear relationship or association. And if you listened very carefully a few seconds ago, I corrected myself when I said we had a positive relationship. I said positive linear relationship. So that word linear is important to describe what the relationship exactly is. Because if somebody says positive relationship, I'm not really sure what that is telling me. If you say linear, okay, now I can picture it. So it is important. Now, on the flip side of this, if we had someone say we have a negative slope, we would infer then as a negative linear relationship or association. And so you've got the two examples here of the points, okay? Again, falling within a line. All right, so one of the exercises we should be able to do is to determine whether or not the points in the scatter plot for two variables are going to be positive, negative, or maybe not follow a straight line pattern. In other words, there is no linear association. So I would encourage you to pause the video and give these four a try. These are excellent questions that could appear on homework, exam, or the final. Okay, let's see how you did. So part A asks the number of hours you study for an exam and the score you make on that exam. Well, in theory, if you study right, the more time you put in studying, your test score should go, hopefully you said up. So I would assume that part A, we would have a positive linear relationship or positive slope. All right, the price of a used car and the number of miles on the odometer. So the odometer, if you don't know, tracks the overall mileage for the lifetime of the vehicle. So as we drive more, that number of miles increases. So what happens to the price of the car? So the price of the car here would be the response variable. Well, the more you drive the car, the more wear and tear, the price of the car is going to go down. So this would be a negative slope or negative linear relationship. Part C, pressure on the gas pedal and the speed of the vehicle. Okay, so what happens with the speed as we press on the gas pedal? Well, the more pressure you put, the faster the car goes. Okay, so this would be a positive slope or positive linear relationship. Shoe size and IQ for adults. I'm not really sure. Does the shoe size, as it increases, does that mean the IQ is going to go up for adults or vice versa? Don't really know. So I don't think this is going to follow a straight line pattern at all for part D. All right, we have some scatter plots and how we would describe their relationship. So starting on the top left, we have a strong linear relationship. That should be obvious because of how close those points lie to a line. The graph next to it has a weak linear relationship. Okay, there still is a linear relationship. It appears positive, but notice that the points are not as close to a line as the previous graph. The bottom left says no linear relationship, okay, and that is because they're just literally scattered. And the last graph says a non-linear relationship. So there is a relationship in the last graph, it's just not linear. Okay, that's why we call it a non-linear relationship. And what happens in this case is it looks parabolic in shape. We would need to use a process known as multiple regression to try to understand that particular relationship a bit more. Interesting extension of this set of sections, but unfortunately we don't have the time. Now, where is all of this going? Well, where this is going is we want to be able to measure the strength of the linear relationship. In other words, we want to put a number on it. Okay, somebody says positive linear relationship, and you say, well, how strong is it? Okay, and you say, well, it's very strong. Well, that's not good enough because your interpretation of what very strong is could be very different than mine. So what we have to do is then put a number on it. And the number we use is known as the Pearson correlation coefficient. And as a parameter, it's rho, the Greek letter rho. We are most familiar with it for the sample, which is R. Okay, and R is a number, and it is allowed to vary between -1 and 1. And as a matter of fact, it can be equal to 1 and -1. So that compound inequality there is showing us that R is locked between those two values, and we would say it's between -1 and 1 inclusive. You might remember way back in chapter 4 about probability rules, probability was between 0 and 1 inclusive. Similar idea here, but now R is allowed to be negative, and that should make sense because we want to be able to extend the -1 values for negative relationships. So if we find that R is positive, then the scatter plot has some sort of positive slope, and the variables are said to have some kind of positive linear relationship. Conversely, if it's negative, then there's a negative slope and negative linear relationship. And if R is 0, then we would have no linear relationship, okay? So if we have the last two graphs, if I can go back for just a second, the bottom two here, no linear relationship and nonlinear relationship, those would have R values that are 0. Both of them would be R is equal to 0. And that's because no linear relationship is present. Excuse me, we have to be careful because the bottom right example that looks like an upside down parabola, that has a relationship, but it is not linear. Okay, that's why the correlation coefficient would still be 0 for that because it's not a linear relationship. Now, if we have something like R is equal to 1, this means that the data are very perfectly in a straight line relationship. Okay, they practically lie on a line, and it would be a positive slope. Similarly, for R is equal to -1, we would have that the value is perfectly straight. Okay, so that is the important thing here. Now, if we have strong positive or negative relationships between the two variables, then we say that they are indeed correlated. Excuse me. So the larger R is, the stronger that correlation is. So in other words, the closer we are to 1 and -1, the stronger the relationship. So if somebody says to you, I have R is equal to 0.1 and R is equal to 0.9, which one has the stronger correlation? And the answer would be R is equal to 0.9. Similarly, if we had somebody say, I have R is equal to -0.99 and R is equal to -0.8, which one has the stronger correlation? That would be -0.99. Okay, so you take the one that has the closer to the 1 or -1. So again, just another representation for that to help you to kind of assess where the strength of the relationship would lie. So again, closer we are to 1 and -1, the better. So what's here are a series of examples that show you various plots, okay, and an estimation for what the correlation would be. And these are obviously computer driven. And there may be some discussion among these. So for example, the bottom two here, correlation of R is equal to 0.9, that looks a bit more scattered than the one next to it for R is equal to -0.99. Maybe the middle one there could be 0.8 versus 0.9. So some discussion, it's ambiguity, if you will, in debate among some of these, but you get an idea of what the values would look like. So obviously, again, the closer those R values are to 1 and -1, the more so that those points begin to really sort of fit or follow a linear pattern. Now, if we had really wanted to scare everybody on the first day of class, we would have showed you all this slide and everyone would have dropped the course, and that would have been the end of Stats 1020. Okay, no, I'm kidding. This is the formula for how we compute the Pearson's correlation coefficient. Okay, it looks scary, but truth be told, it's not so bad. All right, you may recognize on this screen 7 symbols that you have seen before, and that symbol that's repeated here 7 times is big sigma. You may recall that just simply means sum or add. Okay, so if somebody asked me to summarize what we're doing to figure out the Pearson correlation coefficient, I said we're doing a bunch of adding. Okay, as a matter of fact, we're adding 7 times. Okay, so we'll examine an example in a moment that will show you how to use that particular formula. Now, there are some variations on the formula. One is listed above here. Okay, it's actually very similar to the z-score formula. All right. And there's another one version that's a little bit easier on the computation. Now, the SX and SY refer to the standard deviations for X and Y. So obviously, you'd have to know those and compute them out. Depending on the textbook and things that you use, you may see these formulas. So that's why they're presented here, okay? Let me just go back one slide. You'll notice in this one, there's not a reliance on computing the standard deviation, so there's some advantage to using this one over the other two. The one that says and another version is actually a little easier for computation by hand. Okay, so there are trade-offs to each of these. The example that we're going to look at here is to figure out what the correlation coefficient is between the femur and humerus bones. We have 5 measurements here, and I think these were for dinosaurs, if I remember the context of the example. So we're going to declare the X variable here to be the femur's length in inches, and Y will be the humerus's length in inches, okay? And so in order to compute this, what we have to do is, well, you don't have to, but I use a chart. And what I do for the chart is I derive the values for the sum formulas, okay? So if you remember back in a couple of slides ago, there were a number of different sums that we needed to compute. So the first thing when we write out the chart is I want to write in the X and the Y variables, okay? The values for the X's and the Y's. So Xi here is the X variables, the independent, the explanatory, and the Y here is the dependent response variables. It is important that you make sure that they are paired correctly. So for example, 59 and 70 is how they are listed in the chart. We don't want to mix this up, okay? So in other words, don't put 59 with 63. It's going to mess up your computations. The next column says we take the product of the two, xi times yi. So you multiply the two. So 38 times 41. This next column says that you square the x. So 38 squared would be 1,444. And then the last column there is that we square the y's. Okay, so 41 squared is 1681. And we repeat this process for each of the rows, thereby filling in the table. Now, the very last row you'll notice is darkened in, and this is where we obtain the sums. So the sum of all the x's is 291. The sum of all, that should say yi's, is 330. The sum of all the x times y's is 20,040. The sum of all the x squareds is what that should say, is 17,633. And the sum of all the y squareds is 22,790. Okay, so these are the values that we need then to fill in our formula. So what I've done is I've captured that row, so it's just repeated here, okay? And this is the substitution for what that looks like. So n refers to the number of pairs that we have, that's 5. And in the numerator, we have to multiply n times the sum of the x times y's, okay? Well, that was 20,040. We have to subtract from that the sum of the x's, that's 291, and then we have to multiply that by the sum of the y's, which we said was 330. So that's the numerator. In the denominator, we have n again, which is 5, and we multiply that by the sum of the x squareds. So we squared x's, and what did we get? We got 17,633. And we subtract, and this one we have to be careful. This says the sum of x's squared. That is different from what we just did, which was the sum of x squared. So let me repeat that. So we had sum of x squareds. That was our 17,633. This one, we want the sum of the x's squared. The sum of the x's squared is 291. So 291 squared, okay? And we repeat that process for the y's, okay? We run that in the calculator very carefully, and we end up with 0.994, okay? And if I were to interpret this correlation coefficient, I would say, oh my goodness, that's practically 1. There's a very strong linear relationship here between the femur's length and the humerus's length in inches. And there are no units associated with the correlation coefficient, so we leave it as 0.994, okay? All right, now there is something that the book talks about, which is known as statistical significance, and this is important to look at. So it says many times we are tempted to say that because the linear relationship between two variables is statistically significant, a change in one variable must cause a change in the other. However, the world is much more complicated than that. When we do have a correlation between two variables that is statistically significant, such as in the last example with 0.994, one of at least 4 different things may be going on, as illustrated in the figure on the following slide, okay? So we have this idea of correlation. Is this implying causation? So a strong relationship between two variables does not always mean that changes in one variable cause the changes in the other. So the relationship between two variables is often influenced by other variables lurking in the background. And the best evidence for causation comes from randomized comparative experiments. So what is all this telling you and I? What it's saying is just because two variables are correlated does not mean one causes the other. The only thing that explains causation is an experiment, okay? The only thing that implies causation is an experiment. So that's the only thing that can definitively say that we have a cause and effect relationship. Now, people might say, well, why do we have to do all this stuff with correlation then? Well, it is evidence to suggest a relationship exists, okay? I don't want to waste the time with the experiment if I don't have to. So if I compare the two variables and I find Pearson's correlation coefficient and I find that the correlation is 0.003, then it suggests that there's no linear relationship. Then there's no point of me running an experiment then, okay? So it's kind of to give us some evidence whether or not to do it or not. Now, these are the 4 possibilities that could be happening when we have variables that we think are correlated. The first one is the one we hope for, and that is that variable x is indeed causing y. Okay. The second case is actually the converse of that, and it is that y is causing x. Maybe there's a reverse sort of relationship. Okay. The third is that x is causing y, but there's also a lurking variable in the background, z, and that has influence over both x and y. So you might say, well, what's an example of that? Let's think back to the quarterback rating for a moment, okay? So number of passing touchdowns, X influences the quarterback rating Y. What then could be something that also influences Z? How about an injury, right? If the quarterback has an injury, isn't that going to influence both the number of touchdowns that they throw as well as the quarterback rating? Okay, so maybe the quarterback still plays with the injury, but the injury hinders them in some way. So right, so it kind of causes a little bit of an issue. The last one is that the X variable, the explanatory variable, isn't causing or doing anything to Y, but Z is influencing them instead, right? So Z in these instances would be considered the lurking variable. So when this lurking variable sort of clouds what's happening, this is a phenomenon that we know as confounding. And we don't like confounding. It's not good. We want to be able to see very clearly what's going on between two variables. So confounding is a problem. So that is sort of the verb here, right? That's the action that's going on. The confounding is clouding everything, all right? So Star Wars reference, it's like the dark side of the Force, right? It clouds everything. So we don't want that. Now, associations can be explained by a direct cause and effect link between the variables. Okay, so again, the first one there, the X causes Y, that's known as a causation. We have this X is linked to Y, it's causing Y, but Z is also influencing both. We call that a common response. And then this idea of, okay, X is causing Y, but Z is also doing something. So we have this, again, this idea of confounding. So we have to be careful with that. Now, people often wonder, well, then how do you deal with confounding if that's the case? Sometimes an experiment can help with that. So if you have these lurking variables, that's where having a control group is helpful. So for example, if I was going to run a study on seeing whether or not a particular study tool was going to be beneficial to my classes, and we implemented it. So one class would use the study tool and one class would not. One of the lurking variables would be perhaps the time of day that the class runs, who's teaching it, the format. So in order to control for those lurking, and there could be others, in order to control for those lurking variables, what we would do is we would offer the class on the same day, or maybe different days, but at the same time with the same instructor, same classroom, same format. Okay, so try to control for as many of those lurking variables as we can. Someone might also argue, well, what about the makeup of the students in the class? Maybe there's more upper division students than lower division students. Okay, well, we try to then make sure that the classes are equally balanced in that way, maybe equally balanced with majors, right? So you can get out of hand trying to control for so many of these things, but these are considerations that researchers have to do all the time to try to control for these various lurking variables. So it is something that we have to think about and think about rather important. Okay, so again, getting back to this idea of does X influence or cause Y? Again, what this slide is telling us is we have to be careful because there may be other factors that are controlling the relationship between X and Y. So we have to be mindful of those. We have another computation that we can do. This one is much easier, and it's known as the coefficient of determination, and we call it R squared. This is a measure of the proportion of the variation in the response variable Y that can be associated with the variation in the explanatory variable X. Okay, so let's see if an example to illustrate this. So suppose we have the correlation for the number of rooms in houses with their prices, okay? And so this would be R is equal to 0.65. So the question here is how much of the variation in house prices can be associated with the variation in the number of rooms in the houses. So the number of rooms would be the X variable, and the price would be the Y variable. And that should make sense because potentially the more rooms a house has, the more space it's taking, the price goes up, okay? So a lot of things with homes is based on the size, right? And number of rooms. So what this question is asking us very sneakily is what is the coefficient of determination? But look at the wording here. How much of the variation in house prices can be associated with variations in the number of rooms in the houses? So what we need to do then is to compute the coefficient of determination. So what it's going to tell us is going to be the proportion or percentage of the variation in the house prices that's associated with variation in the number of rooms. So we just simply take 0.65 and we square it and we end up with 0.4225 as a value. So the interpretation of this is as follows. We say thus approximately 42.3% of the variation in house prices can be associated with the variation in the number of rooms in the houses. Okay, now people will ask, is that a good thing or is that a bad thing? Well, obviously the higher the correlation coefficient, the higher this percentage will be. And so you want to be able to predict more of the variation if you can, okay? Obviously, the smaller that number is, maybe the worse it will be. Again, depends on the context or perspective that we're trying to understand this situation with. All right, we move next into 12.2, which deals with linear regression. So it is an extension of what we've been talking about so far, but this time we try to do some inferential statistics. And it's not anything crazy like the hypothesis tests were, or maybe you thought they were okay. There is a bit more computation to do. But this time, what we're looking at is actually building a model, okay? Because we want to make some predictions with our data, and that's an important thing to be able to do. Now, in order to make some predictions, we have to use what's called a least squares regression line, or LSR line, LSR equation for short. It's based around the linear equation. You all might be familiar with y equals mx plus b. Well, there's a slight change here. First, we use y hat, and the first question people ask is, why now are we using y hat? Why not y? It's to remind us that this is a model. It's not perfect. It has flaws, okay? So we use this to make predictions. So that's why we use y hat. You'll also notice that we did a little rearrangement. Instead of writing it as mx, it says b1. Okay, so b1 stands for the slope, and b0 is the y-intercept. Okay, so a little bit of a different language on the statistical side that we use. Now, of course, we have formulas for each of the slope and the y-intercept, which is based on the data. So this is the formula for the slope. It has some familiar components to it, because if you remember in the computation for the correlation coefficient, some of these values, like the sum of x's, sum of y's, sum of x squared, sum of x times y, those values are used again in the computations for both the slope and the y-intercept. So a little bit of familiar territory here that we can use some of those computations that we did in the previous example yet again. So that is an added bonus to this. You'll notice that here, this is the y-intercept. This relies on the slope. So you do have to find b1 first in order to get the y-intercept. Okay, and there are a couple of other versions of the computations for both the slope and the y-intercept. So again, we have one that relies on the standard deviations. Okay, these can be a bit more tedious in the computations unless you already know them or have that information. So again, depending on the statistics textbook you use, there are other variations that that are possible. Okay. Now, before we can dive into actually building the LSR equation, we have to know whether or not the correlation coefficient is statistically significant. In other words, do we have a linear relationship between the two variables, either positive or negative? If the answer is no, then we're not going to bother wasting our time building a least squares regression equation. Okay, why would I try to build an equation, a linear equation, for something that does not have a linear relationship? So we need to make sure that we have a strong linear relationship, either positive or negative. So it's important to know what R is, okay? And if we have the scatter plot to kind of help us as well, that is very useful, okay? The question that comes up is, what if we don't have a linear relationship? Well, if there is a relationship, maybe it's parabolic, then we have to use another statistical tool, like I said, multiple regression. If it just turns out that the points are just scattered everywhere, then there's really nothing we do. We just accept the data as that, and we move on and do other things with our lives. Let's return to our example about the femur and the humerus that we looked at before. So we had the explanatory variable being the femur's length in inches, and the response variable was the humerus's length in inches. And these, again, are the sums from the chart that we had a while ago from the computation of the correlation coefficient. So in order to get the computation for the slope, we take n times the sum of the product of the x's and y's, that's our 20,040, and we multiply the sum of the x's times the y, and we subtract that from the value we compute. And then in the denominator, we have n times the sum of the x squareds, which is 17,633, and we multiply, or excuse me, we subtract that the sum of the x's, which is 291, and we square that value. So the slope ends up being 1.197. So this really becomes easy once we know what the sums are. It's really not so bad. Okay, just a lot of adding. In order to get the y-intercept, what we have to do then is we rely again on the slope. So we take the sum of the y's, which was 330, and divide by 5. We subtract the slope, 1.197, and we multiply that by the sum of the x's, 291, divided by 5. And so the y-intercept here is negative 3.665. Okay, so there is the LSR equation. All right, beautiful, wonderful. All right, so question we sometimes will ask, I've been known to do this especially on exams as well as the final, is how do we interpret what the slope of this LSR line? What is the slope actually telling us? So in general, what we say is for every 1 unit increase, whatever the unit is, okay, in this case, it would be an inch. So for every 1 inch increase in, what's the x variable? This would be the femur. So for every 1 inch increase in the femur's length, we see an increase, since the slope is positive, an increase in the humerus's length by 1.197 inches. Okay, so that's the value of the slope. So once again, for every 1 inch increase in the length of the femur, we see an increase, because the slope is positive, in the length of the femur by 1.197 inches. So that is how we interpret what the slope is telling us. So we increase the length of the femur. What does the humerus do? The humerus also increases, and it increases by 1.197. Now, someone will ask, what happens if the slope is negative? Well, then it's going to decrease. Okay, that's no problem. So there's still a 1 unit increase for the x variable, but then the y variable would decrease. So it does depend on the sign of the slope. Okay, and so there's our sentence if you need to see it out for the purpose of your notes. All right, there are some follow-up questions that we can use with this, and this is typical for an exam, final exam, etc. So using this equation, let's try predicting, right? That's the whole point of this. We get this wonderful equation, we want to do some prediction. So the first one here is, what's the humerus's length if the femur has a length of 0 inches? Okay, so you have to remember that the femur here is the x variable. So we plug in x is equal to 0, and we get negative 3.665 inches. That should make sense. That's the y-intercept. Okay, right? If you remember, if x is 0, what's y? Well, it's the y-intercept. All right, very good. But we had a problem. Does that make sense? Can we have a femur's length being negative? You might say, well, wait a minute, can the humerus be 0? Is that even possible? Or excuse me, if the femur is 0, is it possible that the humerus could be negative 3.665 inches? Is this even possible? So interesting. We need to think about this. Part B says, what's the humerus's length if the femur has a length of 61? Okay, so let's see where 61 is. We put this into our equation. We get 69.352 inches. So does this seem reasonable? Okay, well, if I look at my data, I see that the femur has lengths of 59 to 64. So 61 fits in there. Okay. And I noticed that we have 69.352. So is that quite between 70 and 72? No, but it's close. It's close to 70. You might say, well, why is there a little bit of variation there? Well, remember, this is a model. It's not going to be exact. In other words, if I put in 59, that doesn't mean that I'm going to get exactly 70 out using this model. It's a model that's used for prediction. It's based on all of the data, not just some of it. Okay, fine. In part C says, what's the humerus's length if the femur has a length of 130? Well, we end up with 151.945 inches. Okay, so there's a question here about parts A and C. What do we notice? What you should notice is that the lengths of the femur, 0 and 130, that is not within the data range that this model was based on, right? 0 is way outside of this, 130 is way outside of this. This is a phenomenon known as extrapolation. This is where we run into a problem with the model. This particular equation is only good for modeling data that's within the data range. So in other words, 38 to 74 inches. That's the only range I can use to make predictions for the length of the humerus. Anything outside of that, and we start to get things that don't make any sense. Now, someone might ask, well, how then can we get a model that would be good for making prediction for, let's say, 130 inches length of the femur? And my response would be, well, go expand your data set and redo the model. In other words, recompute everything and get a new LSR equation. So this LSR equation is very much so dependent on the data that you collect. So if you are working with someone and you're both collecting data on the same population but different samples, your LSR equation will look different. There may be some similarities, but it will be different and used differently for prediction. So we have to be aware of this phenomenon. Okay, very, very important. Now, we also have one other issue that has a tendency to come up, and that is the issue with outliers, okay? So this is data that shows 24-hour precipitation in inches, and then the maximum annual participation. I think this is for 50 states, okay? Now, if you notice, the red line that's there is for all of the data. That's what we call the LSR equation, or the line of best fit. LSR equation is sometimes called the line of best fit. And you'll notice at the top is Hawaii, HI. Okay, Hawaii is a clear outlier. All right. The dotted line shows us what the LSR equation or line would look like if we excluded Hawaii, which is a very clear outlier. Now, people often wonder, well, what do we do in cases like this? If I were to report this data as a researcher, I would use the dotted line and I would put a note underneath the graph to indicate that Hawaii was indeed an outlier in this case. And for the purposes of the statistical analysis and discussion that follows, it would be with excluding Hawaii in that conversation. So it is possible that outliers will cause issues with the computations for both the correlation coefficient as well as the least squares regression line. So you have to be cognizant of these outliers. Now, we do have some cautions that, again, we've talked about a bit more. So, if we're going to use that LSR equation, there are some things that we should avoid. So first of all, if the data doesn't fall in a linear pattern, we shouldn't be using a least squares regression equation at all, okay? If the correlation coefficient's not statistically significant, in other words, the data does not fall in a linear relationship, okay? Number 3, you're trying to predict something outside the range of the sample data. Okay, that was illustrated a few moments ago. And number 4, the population is different than that from which the sample data were drawn. Okay, so if I were trying to make predictions about final exam scores from, I don't know, a sample of students who are at Wayne State University, and I decide to use that model to make a prediction for students who are taking statistics at Harvard, right? Well, it's two different sort of groups of students for obvious reasons, right? Okay, so Harvard has different set of standards for admissions, et cetera. Their course could certainly be more rigorous. Format could be different. Instructions could be different. Types of topics covered, et cetera, could be different. So we have to be careful then. There has to be a good match between the groups of individuals. And that's not to say that what we offer at Wayne State isn't good enough, but it is a course that is meant to meet the needs of the students that we have, as well as the programs that we offer. And if we look at a school like Harvard, their offering is going to also be different because it's going to be based on their students as well as their programmatic needs. So we have to be careful, okay, with how we're choosing to use that particular model. And this concludes chapter 12.